Hello, Professor Politoed here, and let's talk about geology. Today, we're talking about glaciers and the effects these large sheets of ice have on landscapes, otherwise known as glacial landforms. This video is going to be very Canada focused, as Canada is world class for glacial landforms, and I also live here. This is also kind of my personal love letter for Canadian landscapes. If you don't know me personally, I'm a Virgo, I love being near water, and I hate mushrooms. And I've worked as a geologist in the Canadian Arctic for the last 3 summers, and glacial effects and landforms are literally all across the country, not just in the Arctic. Many of Canada's glacial landforms originate from the growth and movement of the Laurentide ice sheet, which began to form at the beginning of the Pleistocene epoch 2.6 million years ago. But let's take a step back for a second. Did you know ice is technically a mineral? No, really. There are 5 distinct qualities that define a mineral as a mineral, and ice fits into all 5. Those qualities are a defined crystalline structure. Ice has a defined crystalline structure, as frozen water has a defined arrangement of atoms that will always form when water freezes. Solid at room temperature. I can take an ice cube out of the freezer, and it will remain as ice for a time until it melts back into water. It doesn't instantly change into liquid water at room temperature. A distinct chemical formula. Frozen water will always have the empirical formula of 1 oxygen and 2 hydrogens. This is the basic chemical formula for water. Inorganic in origin. Snow, hail, we find naturally forming ice everywhere, not produced by an organism. And naturally occurring. Like the last point, ice forms from the natural process of the weather getting cold. I find this fact super neat, and because of this, glaciers can possess some geological qualities typically found in large rock bodies, such as internal deformation and creep. But for now, let's move back onto glaciers. So how do glaciers form? From the cyclic seasonal changes of cool weather to warm weather, where the beginning of glacial formation begins with snowfall. The amount of snowfall that occurs during the colder months must exceed the melting that occurs during the warmer months. Thus, snow can build and accumulate during the colder months. With this successive buildup of layered snow, the deeper and older layers of snow are compacted and compressed into ice, forming a glacier. And to talk about glaciers, let's bring out my friend Avalugg. Avalugg is an ice-type Pokemon introduced in the 6th generation of games X and Y, and is essentially a large block of ice. Their ancient cousin, Hisuian Avalugg, is also a large block of ice, but contains rock material inside its body. Because of their ice morphology, we can assume both Avaluggs form very similarly to how glaciers form naturally. Hisuian Avalugg has a bit more detail that I will go into later in the video. The most notable feature of this Pokemon are the large cracks in its ice found on their back, mentioned directly in the Shield Pokedex. While the cracks seal on Avalugg every night, these cracks can be found in some real-world glaciers, resulting from rapid glacial movement known as glacial surges. Glaciers appear to be solid blocks of ice, but in reality, they're constantly moving and melting very slowly. When glaciers sit on top of bedrock, geothermal heat produced in the Earth's core will rise to the Earth's surface and begin to melt the bottom of these ice sheets, allowing for the glacier to move and glide across the rock it's situated on top of. We can think of it like an ice cube melting on your kitchen floor, and how easy it is for it to move and slide around. The heat contained in your floor begins to melt the side of the ice cube that it's touching, much like the geothermal heat contained within bedrock, where the ice cube and glacier would have the same movement and sliding properties because of this relationship. This movement is most evident with glaciers found within valleys and fjords, otherwise known as valley glaciers, where they commonly appear as rivers of ice. Glacial surges are cases of short-lived, accelerated glacial movement that is most likely caused by glacial stress. This is where the weight of the accumulating snow and ice is too heavy for the bedrock to support the glacier, giving away the supports the glacier had with the underlying bedrock and rapidly flowing. These surges are rapid and periodic, separated by long periods of inactivity and producing large cracks and crevices as the ice rapidly flows. The cracks found on both the Avaluggs must have originally been a product of this form of rapid glacial movement. Avalugg is colloquially known as the iceberg Pokemon, and valley glaciers commonly form icebergs at the end of the glaciers themselves. The valleys and fjords these glaciers form in typically end at the ocean, and when glacial surges occur, lots of ice is pushed into the ocean to form icebergs. Now, let's talk about Hisui and Avalugg. In my Geology of the Sino and Hisui regions video, I received this comment. Hisui and Avalugg make no sense. If anything, they should have been more icy, maybe having a peak instead of a flat top. Instead of looking like a lightly frosted bug thing, based on what we see in Legends Arceus, the frozen fjords and tundras they call home appear to have shrunk, as you'd expect from the effects of global warming. So why is it not adapted to better camouflage itself? It's not like it was an apex predator with no need for such a tactic in the past. You, at JacobL228, I appreciate the comment. You were the inspiration for this whole video, but to correct you on one thing, I want to explain why Hisui and Avalugg does make sense. So, we have already talked about how glaciers move, melting that occurs at the bottom of the glacier from geothermal heat. But glacial movement also strongly affects the surface of the bedrock the glacier sits on, acting like sandpaper and ripping up a lot of the underlying bedrock. The ripped up rock can become incorporated into the glacier itself, or more commonly will form into structures known as glacial landforms. Going back to the glacial surge images, these lines of rock within the glacier are an example of glacial landforms and are known as moraines, which is just accumulated rock material pushed from glacial movement in these environments. Another common glacial landform are eskers, which are ridges of sand and gravel that form in subglacial channels. Because the bottoms of glaciers are always melting, meltwater accumulates and forms rivers that flow beneath the glacier. An esker is a product of this, where ripped up rock material can find its way into these subglacial rivers, and when the glacier fully melts or retreats, the rock material is left, forming an esker. Sometimes eskers don't form in meltwater channels because the flow is too rapid. In these cases, the water begins to dig into the underlying bedrock and form deep channels. There are many different glacial landforms, some of which I will touch on later, but commonly they form from the ripping up of bedrock from glacial movement. Before we talk about Canada, let's look at a place I'm sure we've all been to, the Alabaster Icelands. I love talking about the geology of the Sino region. I highly recommend checking out my Geology of the Sino and Hisui regions video if you haven't already. And there just so happens to be some glacial landforms in the Hisui region's Alabaster Icelands. Scattered across the low areas of the Icelands are these ridges and mounds of rock material, which I would argue are eskers. Forming in channels under the glacier due to the flow of melting water, we can even go into some of these subglacial channels that dug into the underlying bedrock, which is where Hisui and Zoroa spawns. Looking towards the mountains that surround the Icelands, we can see ridges of rock material trailing down the mountains, which I would argue are moraines, forming from large flows of ice pushing loose rock material into these lines as the glacier slowly moves downward. Moraines can be straight or squiggly depending on how the glacier moves, and a mix of both can be seen in the Icelands. Back to the real world, glacial landforms are found all across Canada, as the Laurentide ice sheet, which was at its maximum roughly 18,000 years ago, ripped up kilometers of surface rock, flattening and smoothing the surface down. This smoothing down of rocks is known as glacial rounding, and it can be seen literally all across the country, from West Coast British Columbia, Northern Ontario, and the Northern Territory Nunavut. Looking at the smooth surfaces produced, we can typically track glacial movement by some of the features left behind. The common ones seen on most of these smooth surfaces are glacial striations, and these lines are really just grooves left in the bedrock surface as rocks contained within the glacier have scraped by on top. Glaciers really do act like sandpaper.
Hi, how's it going, everybody? I'm here in the Killarney Provincial Park and hiking the Crack. Killarney is a world class when it comes to glacial landforms and glacial products of glaciation. And right here, all around me, there's a few glacial landforms I want to talk about. The big one that I'm sure you can all see is how round and flat all of the rocks are around me. And that's when a glacier was going over, ripping up a bunch of the rocks on top and smoothing down the surface, much like sandpaper. And so if you come over here, there's a couple of landforms. These ones are really cool. These are called chatter marks. And so there's two different types of chatter marks. There's crescentic gouges and crescentic fractures. And so crescentic gouges are these half moon semicircle structures right here. And so as these form It forms from rocks that are inside and held within the glacier itself, and as the glacier is moving across the surface bedrock, that rock is getting shoved into the bottom bedrock and creating those gouges, these crescentic gouges that you can see right here. And so the other form of chattermark is crescentic fractures. So they're a little different. They look very similar, and you can actually see some right over here. And so as rocks are being dragged across the surface bedrock, it's forming those glacial striations. And if the rock is deep enough forming that glacial striation, these little cracks, very similar half moon.
Whoa, sorry. I didn't finish my thought. Crescentic fractures form from glacial striations that form with a deep groove. If the cut is deep enough, these fractures will form on the boundary of the striation.
Half circle structures that are moving across, but they're a little bit different. They're a little bit smaller, and instead of the U pointing the way of direction for glacial movement, much like our crescentic gouge right here, the crescentic fracture, which is a byproduct of our glacial striations, forms in the opposite direction. So they look very similar, but the difference in pointing of direction is the main difference between these two. Here I am walking up this nice smooth rock, doing a bit of a voiceover here because, well, this is what it sounds like. Yeah, so doing a bit of a voiceover. So yeah, looking at glacial striations. So when rocks are being dragged across the rock surface, they're leaving these lines or grooves as they dig into the rock surface, and those are what those parallel lines that you'll see running right across the smooth bedrock surface. And yeah, so what do you think about that, Dr. Reginald? Yeah, I agree.
In short, Hoowever and Avalugg does make sense at Jacob L228, considering the sheer amount of rock material that becomes incorporated into moving glaciers. But let's take a closer look at Hoowever and Avalugg. The rock material found on their feet looks very fine-grained and homogeneous to me, which makes me think that this is till. Till is a substrate produced from glacial movement, where rock material ripped out of bedrock becomes ground down into basically sand. The glacier moves on top of bedrock, and any rocks caught in between these two bodies are broken and ground down into basically sand. Till is commonly sampled for mineral exploration, mostly done in the Canadian Shield. This is because it best reflects the primary composition of the source bedrock for ease of prospecting, when combined with glacier direction of travel. Till can be present in different forms, where the most common are mud boils. Mud boils form as a product of the melting and refreezing of permafrost, where the cycle removes large rocks in local areas by having ice push the finer till material upwards and acting like a bubble, and forming these circle structures entirely made of till. But back to Avalugg. Their legs look like they're made of a fine material as opposed to large boulders of rock, so I think that this is till. I want to talk about one more glacial landform before we move on, and those are glacial erratics. Have you ever walked around outside, walked around the forest, touched some grass? Have you ever done that and come across a random large boulder or a collection of boulders just laying around with no reason for them to be there? These are most likely glacial erratics. These are rocks that have been ripped out of the bedrock as the glacier grinds away at the surface and incorporates them into the glacier. As the glacier melts or retreats, the rock is exposed and left as is, often hundreds of kilometers away from its source. As the Laurentide ice sheet began retreating across Canada, many of the stones incorporated into the glacier became released and are just scattered all across the land. I took this video in Nunavut, and those round stones just sitting around are all glacial erratics. The rock they're sitting on, you'll notice, is nice and flat from the constant rounding of glacial movement, but up there these erratics are just scattered all across the land. Many of the erratics in the Nunavut tundra are stromatolite fossils coming from Bathurst Inlet, and where I found them is about 140 kilometers away west from their source. When the glacier retreated, all of those stones were just placed on top of the surface bedrock. What's really neat is that sometimes these erratics are placed on top of beds of other smaller rocks, which will eventually weather away mostly, leaving just the larger ones that are supporting the erratic, which often makes them look like they're balancing on just 3 or 4 tiny stones. So we've talked about how ice affects rocks at the surface. Now let's talk about ice that forms underground. Permafrost refers to this, where permafrost is a layer of sediment or rock that remains mostly frozen throughout the year. This map shows the distribution of permafrost across the globe, where permafrost is strongest in the dark purple and dark blue areas. There are also a few landforms produced from permafrost I want to talk about, the first being frost wedging. One of the main qualities of ice is that ice expands when water freezes, where this is the basis of frost wedging. Permafrost refers to layers of rock material that remains mostly frozen throughout the year. However, during the summer months, the surface 0.5 to 3 meters of permafrost tends to melt somewhat, known as the active layer, and where many permafrost landforms form. If this melting permafrost water finds its way into rock cracks, it'll refreeze during the winter and expand as it changes into ice, thus expanding the crack. As this cycle continues over time, the landscape can become very blocky and fractured as ice has expanded and broken apart the surface bedrock. Thermal cracking is another landform produced by permafrost, and it's somewhat similar to frost wedging. Permafrost behaves quite similarly to pure ice, and since ice expands when water freezes, ice will also shrink as it begins to melt. When ice is in the form of a sheet, typical for permafrost, the process of melting and shrinking will increase the tensile stress across the entire sheet, where cracking the sheet will relieve this stress. We can see it best represented here on this melting lake ice. It's full of these thermal cracks as the ice within the lake is melting. Because permafrost acts the same way, cracks can form during warmer months and fill with sediment or other material, and refreeze when the environment becomes colder. The cracks will continue to open every time the permafrost begins to melt, forming a polygonal pattern on the ground. They're difficult to see when walking on the ground, so here's some video of them I took from the air. I previously mentioned mud boils, and these landforms are produced in the active layer of permafrost as well. When the active layer begins to melt in the summer, rock material within the permafrost becomes homogeneous and isn't well sorted. As the permafrost refreezes, the more buoyant till material rises to the ground surface and pushes away the larger rocks, forming these circular structures containing only till. This structure will remain through the next cycles of seasonal changes, continuing to circulate and push away larger stones. This is known as buoyancy-induced soil circulation, or mud boils. Although Canada has some of the best examples for these glacial landforms, we can find some relict glacial landforms as far as New Jersey and New York, forming from the Laurentide glacial sheet maximum around 18,000 years ago. In New York, the Cayuga and Seneca and other surrounding lakes are glacial channels that form from erosional processes. Glacial meltwater flowed rapidly under the glacier and significantly through these areas, cutting deep channels into the bedrock and forming these lakes when the glacier retreated. In New Jersey, there are some relict thermal cracking polygons from permafrost scattered across the state, forming during the Laurentide glacial maximum. And they're melting. I feel like I would be doing a disservice to you if I didn't talk about climate change in a video about glaciers. It's no surprise anymore that the world is getting warmer. The summers are getting warmer, wildfires are increasing, the world is overall just getting hot. Since the beginning of the Pleistocene 2.6 million years ago, overall global temperature has alternated from warmer and cooler conditions, where there have been roughly 41 of these alternations over the last 2.6 million years. We know this by analyzing the ratio of oxygen-18 and oxygen-16 isotopes that are trapped within the glaciers themselves, as well as analyzing fossils of benthic forams that lived in the ocean at the time. We can use this oxygen-18 to oxygen-16 ratio to understand the climate conditions during the time of the ice's formation. Higher oxygen-18 concentrations relates to colder conditions and high glacial formation, where a balance between oxygen-18 and oxygen-16 concentrations relates to warmer conditions and little glacial formation. Currently, we are in one of those warming periods, one of little glacial formation. But that's just it, right? There should be some glacial formation occurring, shouldn't there? I've seen this argument before, that we're just in a warming stage, being used to say climate change isn't that bad, or to flat out deny it's happening. But it is. Human activity is absolutely affecting the large rise in global temperatures. The last 10 years have been the worst for this. The unfortunate reality is that there isn't much we can do anymore for the shrinking of today's current glaciers, but that doesn't mean that some people aren't fighting to preserve them. The Ice Memory Foundation is a group backed by 7 countries where they aim to gather and preserve ice samples from the most critical of glaciers. This is to ensure the historic climate and environmental data contained within the glacier is preserved and not lost when the glacier melts away. Other organizations are fighting for the wildlife that call these glaciers home, like Polar Bears International and the Rain Coast Conservation Foundation, which studies polar bears and whales and helps in preservation and protecting their natural habitats. I highly suggest reading into some of these groups, especially Polar Bears International. This is the world's leading group in polar bear conservation, committed to protecting the sea ice these bears depend and live on, raising awareness, and teaching about how this fragile ecosystem is interconnected within itself and to the rest of the globe. Let's go back to history for a second. A note that I wanted to mention is that this main ice block in the Alabaster Icelands is probably the main glacier that caused a lot of the surrounding glacial landforms, and I think it's melting too. Since this area is called Avalugg's legacy, I'm going to refer to this glacier as the Avalugg Glacier. The Avalugg Glacier is situated in the area's lowlands and has eskers completely surrounding it. It only makes sense to me that the Avalugg Glacier was significantly larger and had valley glaciers forming moraines in the surrounding mountains. The Avalugg Glacier then rapidly retreated. Whether that was due to climate change or the natural warming cycle of the planet, I'm not so sure, but it rapidly shrunk to its current in-game size. The surrounding eskers formed under the Avalugg Glacier when it was at its maximum, and the moraines formed when there were valley glaciers within the mountains. We can also see active melting of the Avalugg Glacier with the large size of the underlying caverns within the bedrock, as although channels do form from meltwater flowing under the glacier, they don't get that large unless there is a lot of meltwater flowing underneath. I've mentioned a few times already, but what the heck was the Laurentide ice sheet? For North America anyways, this ice sheet was the massive glacier that was present during our last global ice age, when mammoths and saber-toothed cats were alive. The ice sheet began forming and growing at the beginning of the Pleistocene epoch 2.6 million years ago. This was the beginning of a cold stage with high glacial formation. Glacial growth continued until the Laurentide ice sheet reached its maximum, the largest size it would reach around 18,000 years ago. At its maximum, the Laurentide was roughly 13 million squared kilometers, which is similar to the ice sheet of current-day Antarctica at 14 million squared kilometers. This is the extent of the glaciation across the globe at this time. We can see it affects countries like Norway, Finland, and Sweden, and the northern part of Russia. On this side, it's only just Canada and Greenland that's glaciated. Down here, we can see that glacial ice began forming in New Jersey and New York, explaining the relict glacial landforms left over in these states. Over time, the Laurentide begins to shrink, splitting around the boundary of the Yukon and the Northwest Territories and British Columbia and Alberta, forming a channel that is thought to be the pathway for the first human migration in North America. We know that the ice splits and retreats this way by tracking sediments left over from the lakes that begin forming on the glacier edge, as well as analyzing glacial landforms for glacial movement. The Laurentide continues to retreat until 1,000 years ago, when the size of the Laurentide is what we would expect for today. This year, I had the chance of working in the Canadian Arctic above the Arctic Circle, and what's super cool about that is I saw a lot of the glacial landforms I talked about in this video on a daily basis. For a lot of my geology videos, it's sometimes hard for me to get actual footage of what I want to talk about, so I often just use Google Images. A lot of the footage you have seen in this video I have personally taken, and it's honestly been a trip working in this environment while planning and making this video. For glacial rounding, the best place I have ever been to see this wasn't in Killarney, but up north on the Arctic coast. One afternoon this summer, a few coworkers and I went to the Arctic coast in Grays Bay, and I was just shocked at how gorgeous this place was. Steep cliffs, light blue water, this place was beautiful. The beach we went to was all solid rock, and it was just completely smooth and flat, caused by the high amount of glacial ice and sea ice that has traveled across this beach, constantly just wearing and grinding down the rock. Here I am looking pretty, and looking closer at the smooth rock surface, it's just covered in glacial striations. The blocky and fractured nature of the surface rock can be attributed to frost wedging, and the large random round stones on the beach are glacial erratics. Thanks for checking out my video, and a big shout out to @JacobL228 for inspiring me to make this video. Glacial geology isn't something I've thought too much about, nor really cared about. To me, it's always just been lines on a rock or dirt. Making this video and showcasing some of these glacial landforms, glacial isn't that bad. Maybe it's a case of me growing up around this stuff that's caused my disinterest. Glacial landforms are literally all across the country, but glaciers were an important part in shaping our current landscape, so maybe just that makes them pretty cool. For a final note, Hisuian Avalugg does make sense, and the loss of its rock type over time with regular Avalugg could represent the shrinking of glaciers due to global warming and the little impact current glaciers have on surface bedrock. But again, thanks for checking out my video. Be sure to leave a comment down below if you learned anything new, and I'll see you in the next one.
Penis. Ball liquor.
Just another big truck.